Yeah, we definitely need to get together to talk about all the mysteries of range reduction and the different strategies that have come up over time.
Right. Yeah. For our current project with Ian, like we need like a taxonomy of all range reductions.
Yeah, the taxonomy is easy, right? So like there is additive range reduction, multiplicative range reduction, and but the nuances and how do you like even like divide your interval is kind of pretty interesting. So for a
okay. Yeah, so I mean, okay, so the taxonomy is easy for like traditional functions, right? If you want to implement libm, right? Sine is additive and log is multiplicative, but I think one really attractive aspect to having good tools for synthesizing math libraries isn't like sine of x. Is like you need an implementation of some kind of wacky function, right? Like sine, well, say you need 1 minus sine of x, right? That's like you're not going to get, it's not going to be quite as accurate if you actually do the subtraction, but you can, if you could synthesize a function to do that, and like, okay, so the Solya tool can do that, right? I think Jay's work can do that, but you still need to come up with a range reduction from scratch. So I mean, I think of the range reduction question as being like, here's a function and we know a bunch of mathematical facts about it. Maybe it's periodic, maybe it's symmetric, maybe it's even or odd. And you want to go from that to a range reduction. I think that's a really interesting problem. That's like a synthesis problem where you start with the spec and you want to learn something. It's not that you're synthesizing the function, you want to synthesize the range reduction, which is this really like interesting mathematical puzzle.
Yeah, it's a hard problem. Like initially we thought about this, but we did not succeed. So, so like Jay's first idea was, oh, let's synthesize range reductions, and like again, like we are not experts in this domain, right? So we couldn't come up with a cogent strategy. So it's again, maybe like we need like this unique insight that we don't have to synthesize it. At least like it's beyond the realm of current program synthesis techniques directly. We need something clever. So that's our and
yeah, well, I was surprised. Yeah, go ahead.
In their absence, what Jay has been doing is reading up lots of books like Cody and Wade, Fraser's book, and synthesizing clearly understanding what their insight was and recreating and adapting it to his context. Which has been
the whole thing, right, is that there's like 10 people on Earth who know how to do this whole process, and your solution to this problem is for Jay to become the 11th, which is, I mean, it it works. It's not quite what we'd want, right? It's not really democratizing it. It's expanding it by one more person, but it's what has to be done.
But at least like what we have been trying to do is like make it accessible to the rest of the audience to do this, and this has been our goal in the papers, like make it really accessible so that like people can understand. For example, some of the stuff that we did with hyperbolic functions, they're like pretty standard, but like it's very difficult to understand. So
I have to point out, I really like your copy of Hacker's Delight in the background there. Very recognizable book.
That's fantastic. Good observation, Ian. Yeah, okay, looks like folks are filtering back in, so we've got another minute or two before we kick off the next session, which is enough time for me to grab my pot of tea. Okay, so Peter, you ready to go?
Sure.
Okay, great. Well, we've got a minute, but I've got to just making sure before I introduce you and all.
Yep. Can you see this?
Yep, popped up. Great.
Very good.
I'm glad everyone's putting FPTalks 2021 on the slide deck. I think it, we purposefully picked a name that was a little more approachable than the usual like 4-letter acronym. And now it makes it look like a real thing.
I think given this lineup, I mean, last year was also phenomenal, right? It's a huge draw. It's really exciting. I mean, how often can you just like in one day back to back see so many great talks? It's I don't know, it's a lot of fun.
Well, we're not done yet. So there's more great talks to come. And actually that's a fantastic transition to session 5, which is starting now. And starting off session 5 is Peter Lindstrom. So Peter's a computer scientist in the Center for Applied Scientific Computing at Lawrence Livermore. And in particular, he leads the ZFP and the FPZip data compression projects. Though he's also on the POSIT working group and doing a lot of other things in the floating point and HPC space. So Peter will be telling us today about compressing floating point and how that affects accuracy and performance.
All right. Thanks, Pavel, for the introduction. So yeah, today I'll be talking about floating point data compression. So for those of you who have not heard or know about ZFP, I just wanted to give a brief overview. So I like to think of it as 3 essentially orthogonal concepts. First and foremost, it's a new compressed format for floating point numbers, not for scalars, but for small tensors or small blocks of floating point numbers. And as such, ZFP provides an alternative to traditional IEEE floating point representation, and as well as some of the more exotic ones like B-floats and posits that have come out over the last few years. ZFP also implements C++ classes for multidimensional compressed floating point arrays that are slightly different from your conventional arrays in the sense that you can actually specify the exact memory footprint down to single bits. But ZFP provides an alternative to standard STL vectors or NumPy arrays and whatnot. And finally, you can also use ZFP to perform streaming compression of uncompressed floating point data. So if you're running a simulation generating a bunch of big floating point arrays, you can use ZFP to just compress those arrays before you write them to disk. So the way the ZFP works is that it partitions a d-dimensional array into these small blocks of 4 to the d values. So a 3-dimensional array would be partitioned into 4 by 4 by 4 blocks of floating point numbers. And then ZFP encodes those to a variable length bit string. And naturally, this sort of common blocks of floating point numbers that occur more often will have shorter codes, and that's how you get compression out of it. So ZFP exploits the inherent redundancy or correlation between nearby values that we tend to see in applications such as PDE solvers, for instance. You can then also take these variable array bit strings, which tend to be difficult to work with, and just convert them to fixed length format simply by truncating the array. So that's very much similar to what you would do with a floating point number that represents a real, right? You would just truncate it to a fixed number of bits by discarding the least significant bits. And ZFP works very similar in that manner. ZFP also uses, it's a very high-speed compression scheme. It's based entirely on integer addition, subtractions, and bitwise operations. And it also exploits a lot of inherent data and task parallelism. So it can do the conversion from, say, IEEE to the ZFP representation very efficiently. It also is a very information compact representation in the sense that you get a lot of accuracy per bit stored. So as we shall see later, ZFP typically improves on IEEE floating point by several orders of magnitude in terms of accuracy for the same amount of storage. As I said, ZFP provides these floating point arrays. We have C++ classes that just use operator overloading. They act just like regular arrays. Under the hood, ZFP will do compression, decompression, and caching of these blocks. That's all transparent to the user. The user just sees these as regular arrays. And as a matter of fact, here's an example where I'm showing a small code snippet on the left here using, just your standard STL vectors. And I've highlighted on the right the lines of code that you need to change to work with ZFP arrays. So in this case, we have 2-dimensional arrays of dimensions nx by ny. The user then also specifies how many bits per array element to store. You can also change some of the other lines of code to take advantage of 2-dimensional indexing to make the code a little bit readable, but that's optional. So typically, all you have to change are array declarations. As I said, there's also a streaming compression mode where ZFP allows you to specify relative or absolute error tolerances. There's also a lossless compression mode. We have several different backends implemented, from OpenMP to CUDA to HIP and some of the other ones. Intel has their own AVX implementation of it. We also have an FPGA implementation of this. We support several different languages, C, C++, Python, and Fortran. There are also third-party implementations out there for Julia and Rust and a few other languages. And ZFP is being picked up by a lot of different applications. First and foremost, I/O formats. We have an HDF5 plugin, for instance, that ships with HDF5. Let's see. So how does ZFP actually work? What does it do under the hood? Well, if we're starting with a raw array of floating point data, each block will then undergo what's called a block floating point transform, where we represent all the values within a block with respect to a single common exponent. And then the values then essentially become integers that we operate on. We then perform a near orthogonal block transform that's very similar to the discrete cosine transform that's used for JPEG image compression, but it's actually more efficient and more effective than the DCT. Then we use what's called embedded coding, where we encode one bit plane within the block at a time, from most significant to least significant bit, until we reach the bit budget that the user has specified, or until we reach an error tolerance also specified by the user. And out of this, you get this compressed bit stream. All right, so since ZFP is based on a block decomposition, it's natural to ask, do we actually have artifacts from that, as are pretty common in JPEG image compression, for instance, if you compress too aggressively. So one way that you would expect these artifacts to manifest themselves is if you compute, for instance, spatial derivatives on, say, a 2-dimensional domain. So what I'm showing here is a highly nonlinear 3-dimensional field that we're going to compute the Laplacian of, and it was designed so that the Laplacian would actually be concentric circles. You're also seeing these dark bands that actually represent highlight lines that are dependent on the normal to the isosurface in this case. So those bands are actually dependent on the third spatial derivative. What we're showing here is the ZFP representation of this using 6 bits per value. So we're actually representing the original field and then performing differentiation, right? You can see some minor artifacts here. They're not quite as objectionable if you were to do this with IEEE half precision or using posits or other common number representations. As a matter of fact, ZFP at 6 bits per value is more accurate than IEEE single precision at 32 bits in this particular case. So why is this? So what I'm showing here is an error plot on the vertical axis as a function of the grid spacing. So as we go to finer and finer grids on the left here, as is well known, we're going to decrease the truncation error up to a certain point where the round-off error kicks in. So if you were to do this computation using standard double precision, you would essentially end up with this gray curve here, which more or less is the maximum of these two error terms. With ZFP, we have an additional error term that's related to what we call the compression error, which is just another form of round-off error, but it's what happens when we truncate these bit strings. So what we're seeing here is that this theory actually is really matched well by practice. We're seeing the ZFP curve here in blue using 28 bits per value. Of course, you want to compare that to IEEE single precision. We're seeing several orders of magnitude improvements here. And it's interesting to note that the compression error actually decreases when you go to finer grids. That's because the function gets locally smoother and more correlated. In other applications, such as in PDE solvers, you will introduce error in each and every time step when you compress the data back to memory. And it's natural to ask, will this error blow up over time? It's possible that might happen. So we've actually been able to establish error bounds on the error as a function of time. So we can show that the solution does not blow up. And as you can see, that the actual observed error is still a couple of orders of magnitude lower. So the error is not quite as tight as we would like it to be. But nevertheless, we can actually dial in this and make sure that we use enough bits to stay well below the truncation error. What I'm showing here is what happens if you don't use a fixed number of bits per block, but what if you vary it throughout the domain? You can take advantage of that by not using too many bits in regions that are uninteresting, where few things happen. So what I'm showing here is a little animation of this PDE. It's a hyperbolic PDE. It's a shockwave that bounces off the walls. And what you're seeing here in color is a color coding for each two-dimensional ZFP block here throughout the domain. And you can see that in many cases, we can stick with just 8 bits per value indicated in blue, and only really around the shock itself, where you have a sharp discontinuity, do you need to use 64 bits. Now, if we actually compute the actual error with respect to a double precision solution here, which we call ground truth. So the 3 rightmost images here represent IEEE single precision, then ZFP using a fixed number of bits per value, and finally these adaptive arrays where we vary the number of bits throughout the domain. You can see that for adaptive ZFP, the error is essentially 0 everywhere, where the error is, well, it shows up as a white background, and compared to IEEE single precision, the reduction in error is about 6 to 7 orders of magnitude. Here's another little example where we're showing a shock that impacts a helium bubble. We're comparing IEEE double with ZFP at 16 bits per value, and also comparing that to half precision and posits, also using 16 bits per value. And as you can see, qualitatively, the ZFP solution is almost identical to double precision here, whereas half and posits don't do quite as well. In order for this to work well, you need a really fast scheme. What this shows here is the actual throughput in number of uncompressed gigabytes per second compressed by ZFP. And as you can see, as we go down to fewer and fewer bits per value stored in memory, the throughput actually increases all the way up to close to 500 gigabytes per second. So this was done on an NVIDIA V100 card, where we're taking advantage of a lot of parallelism as well. So the point is that at a few bits per value, as you might want to use, for example, for visualization, you can actually get a net speed up by using compressed arrays just by moving less data through the memory hierarchy. So I want you to focus here just on the bottom 2 images here, where we're comparing ZFP's variable rate arrays, where we're storing less than 1 bit per value, and then render these images from compressed storage in memory. And as you can see, the actual total time here is less than if we were to just store this as 32-bit float. So this actually has a potential to improve performance also. So ZFP is freely available on GitHub. It's distributed under a BSD license. And I encourage you to go out there and play with it. And this is my last slide, and I'd be happy to take questions.
Great talk. Many thanks. We do have several questions here in the Slack. One question. So, are you you're still computing with sort of standard IEEE 754 hardware? The ZFP is used for interchange?
Yeah, that's a very good point. So it's currently just being used as a storage format. And when we want to do computations, we actually do decompress to IEEE double precision currently. We could, in principle, decompress to quad precision if we wanted to obtain even higher precision. We have done some work where we can actually do some computations directly on ZFP, and then you avoid a conversion back and forth between IEEE. You actually reduce the additional roundoff error that occurs when you go between the 2 different representations that way. So there are some things that you can do directly on the compressed representation, or sort of a partially decompressed representation.
Super interesting. So I think I think we were at Conga a couple of years ago, and there was a talk for some telescope guys, and they were talking about how posit might be better for interchange, but this looks like it is even, providing even better results.
Yeah,
super exciting.
Well, posits are a little more general purpose in the sense that they work on individual scalars, and ZFP assumes that you have this continuous or quasi-continuous field that you're representing. But in those situations where that's the case, then ZFP tends to work far better.
Yeah. We got a couple more questions. Johan, do you want to ask live, or I can also read it off? Okay, I'm going to assume I should read it off. So Johan asks, does computing the number of significant digits with stochastic arithmetic to truncate noise bits help to improve the compression ratio?
That's not something we currently do. That'd be interesting. We haven't actually done that comparison, but we do pay attention to rounding, especially in more recent versions of ZFP where we looked into that. It's important for statistical analysis to make sure that you don't bias your errors. So we've paid a lot of attention to that lately.
And there's several more questions. I would take Theo's. Theo's going to speak in a minute. So he was asking how to interpret the error images from the posit computation on the plot a couple slides back. I guess what's the scale? Yeah, on this one. I think.
Yeah, so
no, further down, the spiky bowl.
Oh, the spiky bowl. Yeah, sorry, this one.
Yes. Yeah. How do I interpret that?
So what you want this is to be a perfectly smooth sphere, but because of round-off errors in the derivative computation, you end up with these really fuzzy-looking things.
That's horrible looking.
It's difficult to compute good Laplacians for finally resolved grids. I mean, you'd be surprised. Yeah.
Excellent. Very good.
Yep.
Well, we should switch on to the next talk. I'm really curious also about using these techniques with other formats, et cetera, et cetera. But let's continue that thread in the Slack, and I'll hand it back to Pavel to introduce our next speaker.
Okay, yeah, I mean, right. So thank you, Peter. I think really cool talk and a really cool sort of part of the design space for numerical representations is tensors as a whole, not individual numbers. I think it's going to be more important as time goes on. So our next speaker is Tanmay. So Tanmay is a graduate student at the University of Utah. He works with Ganesh, who many of us know, and he's going to be starting his PhD program this fall. So this is I think a great start to a PhD program. So he's going to be talking about some of his most recent research work, and that's going to cover tools. The tools he'll be talking about, Satire and Seesaw. So Tanmay, please. I think we cannot hear you. Oh, yeah, now we can.
It should be good now. Yeah, thank you for the introduction, Pavel. Hi, everyone. I will be talking about a tool that our group developed. So we call it Seesaw, and you will soon understand why. So Seesaw helps to analyze a round of errors in loop-free programs with conditionals. Hereafter, they will be called conditional programs. You might ask, what do you mean by conditional programs and why they are loop-free? Well, loops are hard to reason about in this context. So we focus on conditionals like if-else statements. That is where Seesaw gets its name from. Here is how the talk is organized. I will summarize the motivation, explain Seesaw in one slide and how it calculates the error. And I will conclude with the results that we got, the contributions of the tool, and the conclusion. So we start by understanding the importance of rigorous methods. When we are testing programs, we generally employ empirical-based testing and ensure that we cover as many test cases as possible. But the problem with empirical methods is that they do not give us insights into the code behavior. We are simply sampling input points and running tests across all inputs. This is where rigorous methods come in. Rigorous methods allow us to define rules following which we can write tests that generalize code behavior across input intervals. In this area, rigorous methods are often used to analyze programs, and progress has been made specifically for straight-line programs. State-of-the-art tools, such as those stated here, are available for error analysis of straight-line programs. However, one problem is that existing tools are not scalable, and so choke beyond a few hundred operators. The second problem is conditional programs. Conditional programs have been studied in many past works, yet we are unable to find release tools that handle conditional programs. Our main comparison is against two rigorous tools that are able to handle these programs. The first is Precisa, which was developed by NASA researchers, and the second is Fluctuate, which is a commercial closed source tool capable of handling loops and has been improving scalability every year. In this talk, I will describe how Seesaw improves upon these tools by handling non-trivial programs. One final thing to note before we start with Seesaw is that it is an extension of our previous work, Satire, which has a publication in Supercomputing 2020. And Satire was shown to have scaled to approximately 4 million nodes, working on condition-free straight-line programs. It is based on a scalable implementation of Symbolic reverse mode AD. Now to explain Seesaw in one slide, we simply need to understand how it is used here. You treat Seesaw as a black box and feed it a large expression DAG with conditionals, along with intervals of values for each input in the format shown here on the left. Each input will have a floating point type. Here we have a FL64, which stands for a double precision type. Seesaw also handles a few other types. And after processing, it will provide you with the maximum absolute error on the input-output variable specified across all points in the input intervals, along with instability jumps. Moving to the workflow. So the parser builds a conditional computation graph using the input from which Seesaw extracts expressions. Error from the nodes in the CCG is propagated upwards to the root of the computation graph using symbolic reverse mode automatic differentiation. Error expressions are generated and accumulated at the root node to get the final output error expression. We then subdivide the input intervals using a tool called real paver for the constraints that we have. This is to handle conditionals to create subdomains over which to optimize error. Optimize for error, sorry. We account for optimization over non-rectangular domains by paving the region with rectangles using an off-the-shelf tool called real paver. This part of the flow is different from Satire's workflow. Finally, these paved intervals, along with the final error expression, are fed to a global optimizer called Gelpia, which gives the maximum bound on the error values across all the input points in the intervals. Seesaw reports this worst case absolute error bound along with instability jumps at different conditions. Seesaw also provides optional facilities to perform validation and additional statistical analysis. Now, let's look at how Seesaw calculates error at the output node in this conditional computation graph here. This error formula can be used to summarize how the error is calculated at the output node. Sn is the expression at the output node, and E of Sn is the error at the output node. The first term on the RHS is the local error introduced due to the final operator, with delta being the round-off error. In the second term, we sum over the errors from the internal nodes. And while doing this, we multiply the forward error at node n with its path strength to include its contribution to the error at the output node. The path strength of an interior node n with respect to the output node is the sum over all paths from node n to the output node. This process happens incrementally using dynamic programming. But what about conditionals that govern which paths are to be summed over? This is a key addition made by Seesaw. How is the error propagated through conditionals, you may ask? The way to handle conditionals and the error generated by the conditional expression themselves need to be included. The expressions involved in conditionals also generate errors, and this must be accounted for. This is accomplished by weakening the conditionals. The summation is written in a symbolic manner and accounts for all the available paths. For this, we introduce the concept of conditional pathwise summation represented by this bow tie symbol. When you weaken the conditional, there are three regions that are created. Suppose the node S9 in the CCG is our output node. Consider the two paths in the CCG created due to the predicate P2. one in orange and the other in green. The bars on the right represent the three regions. The orange one is the true region, the green one is the false region, and when you weaken the conditional, you can see that these two regions spill into each other, creating this blue region of overlap. Notice this funny thing here in the second line of this equation. It has P2 conjugate not P2, which is always false. But since these conditionals are weakened, that is not the case, as it accounts for the error flowing into the computation of the guard P2. The errors in these three regions, therefore, are separate and are activated by the input values accordingly. You can see the apparent benefit of Seesaw from this table, where we compare Seesaw with Precisa and Fluctuate. Our benchmarks come from books such as Real-Time Collision Detection and Essential Mathematics for Games and Interactive Applications. These are geometric computation programs involving conditionals. These are just some selected benchmarks from a full table of results that you will find at this link. You can witness the scalability here. Where Precisa and Fluctuate failed to complete, Seesaw was able to give a tight bound on the error. Seesaw is able to provide more accurate error bounds than both the tools. Further, Seesaw is able to give instability jump magnitudes where Precisa does not, and Fluctuate acknowledges the presence of instability, but not its magnitude. Seesaw has had several improvements over its predecessor, Satire. It retains Satire's scalability of first-order error analysis. Its scalability is similar for codes with fewer or simpler conditionals. The reason this is good is because many geometric codes actually do not involve too many conditionals. For example, a benchmark tightest enclosing sphere has fewer than 10 conditionals. Precisa, on the other hand, runs into scalability issues. Fluctuate is a moving target and improves every year. It executed almost all benchmarks within 0.1 second. Seesaw can give magnitude of instability jumps, whereas Fluctuate detects its presence, and Precisa does not have this functionality. The main related work on zonotopes used in Fluctuate ran into problems with complex conditionals due to the use of transcendentals and nonlinearities, but the tool supports some loops. Seesaw is able to handle complex conditionals elegantly using reverse mode AD by naturally incorporating conditionals within the process. Finally, Seesaw is able to calculate the exact weakening needed for conditionals and so does not end up over approximating the error. To conclude, we are able to plug a major hole by providing a scalable and rigorous analysis tool for floating point codes from practical domains. Seesaw provides facilities such as empirical testing and statistical profiling for cross-validation. This work generated rigorous definitions of reverse mode AD with conditionals naturally incorporated. We will also be presenting this work at IEEE cluster to be held in September, so look out for that. And the link provided in the presentation is not the final version, and it will be revised for publication. Finally, you may find a tool at this GitHub link, and we also have a Docker image for you to try out. Thank you for listening.
Many thanks, Tanmay. One suggestion we have in the Slack I think is really interesting. I don't know if you've looked at any codes from geometry or geometry processing. That's a place where branches tend to be really important and tricky. So you gave the example of the real-time collision detection. Did you sort of see any differences across different kinds of benchmarks where branches were more or less problematic for the worst-case error bounds?
Well, it depends on what kind of conditionals we have. So if the conditionals are too complicated or too big, even Seesaw is sometimes runs into problems. So yeah.
If I can add something to that, yeah, we definitely need to push Seesaw through more examples. So one challenge that Ignacio gave us, correct me if I'm wrong, Tanmay, we could finish that using abstraction. So there are cases where the internal size blow up also. needs to be mitigated by suitably guiding the abstraction on the fly abstraction. Is that correct?
Yeah. So, for example, suppose we have a conditional such as x upon y, and the denominator crosses certain points such as 0 or something, then it might run into problems and might get stuck. So we can handle those kinds of issues by trying to include intervals that should not be considered.
Yeah, and yeah, this is good. And to answer Zach, I think some of these algorithms, this is why I was asking Laura a question saying, is it always possible to find one governing postcondition that explains answers across all the paths? You know, that might be possible in some examples. For instance, some of these geometric algorithms take the conditional and branch to different sub-algorithms, optimal for, say, the eigenvector, eigenvalues, and things like that. So yeah, so it's not entirely clear whether the different branches always produce from one to the other a smooth transition in terms of the outputs, or are we to expect clearly different answers by taking different algorithmic subpaths? So all these are yet to be studied. Yeah.
Nice. Well, I think so yeah, really exciting work. You know, there's a lot of papers that involve floating point verification that ignore loops and conditionals. So it's nice to see, you know, chipping away at people's excuses for not doing those by providing techniques so they can. But I think with that, we will move further discussion to the Slack. And Pavel, all you.
Yeah, great. So, yep, fantastic talk, Tanmay. Everything Zach said is right about the importance of conditionals. So our next speaker is Theo Omtzigt.
Good enough.
Sorry, Theo. I'm not
good enough.
So Theo runs Stillwater Supercomputing, and sort of what Stillwater Supercomputing does, it tries to help people, especially in analytics or big data, try to make use of a lot of this advanced numerics and advanced hardware. So whether that's, you know, GPUs or FPGAs, and you know, adding that to commodity systems so that they can do more complex operations and work faster. And that's kind of what Theo's been doing for the last couple of years, and something he'll be telling us about right now.
Excellent. You guys see my my slide?
Yep, and we can hear you too.
Excellent. So indeed, thanks, Pavel, for that introduction. So the talk I wanted to give here is really sort of to make certain that this layer of arithmetic the community is aware of it, and that we can build on top of it, because for this kind of stuff, what we're presenting here is just the arithmetic layer, but we would need very many different research outputs from the library generation R&D that Santosh and Jay have presented today, as well as Pavel and Ian. Then we have, of course, the whole precision quantification mechanisms that would inform what type of mixed precision selections you would take from Mathieu and Dora, and Nestor's work on Shaman. And then, of course, we have this whole use case and optimization case where we're sort of needing the optimization work that that Brad and Zach presented today. So this is just the numerical layer, and I just wanted to give you guys a quick sampling of the new developments in Universal. So the key point here is that about half a decade ago, the commercial entities that were interested in sort of capturing the Internet of Things were estimating what the world would look like in 2020, 2025. And they all sort of settled on this beautiful marketing number of 1 trillion sensors. You know, all of them were a little bit optimistic, but the point being is that if you really want to drive a instrumentation of the natural world, then you really do need sensors that measured in the millions, trillions of instances. And of course, all these sensors will throw off some information that needs to be processed. And this is really where we are focusing our commercial efforts, is to really think about what this would be for the next generation computer architectures and silicon and gallium arsenide and other type of semiconductor materials that will be used in order to do these smart sensors and the intelligence and embedded intelligence applications that sit on top of that. So the basic structure that embedded intelligence will take shape as is really a sort of a processing pipeline between the sensor data and the actuators that will act on the decisions that intelligent systems takes. And that, if you sort of think about extrapolating to the multi-trillion sensor vision, you will see that if that vision comes to be, that this architecture is really going to be the computer architecture that is going to consume most of the silicon that is going to come out of fabs, right? So this is what most silicon will be used for, and therefore it's clearly going to be a competitive advantage if you can take advantage of the resources provided, because it will mean either higher performance, better features, more capability, or a lower cost. So what really is essential to the quest for maximizing efficiency and lowering costs, which really is sort of two sides of the same medallion. But fundamentally, you need to look at that application. You need to identify how that application does its processing, and then you need to tailor the data structures and the operators to really be within just enough in the bounds of the application. There's another really important aspect, particularly for power, and that is you really need to organize your computation to avoid having to go off chip. So this is research that was done actually by Bill Dolly, who's now at NVIDIA. But it basically this research that he did, he was looking at why GPUs are so much better per flop dollar than CPUs. And it's very obvious, isn't that a GPU comes in with a tiny little piece of information about the triangle, and then it does that transformation, and then it fills in all the pixels of that triangle. So you have a tiny little bit of information, and then you have a 200-300 clock pipeline that is building intermediate values that are processed, never leaving the chip. So that fundamental organization is really something that makes a huge difference in power efficiency, and that will definitely impact how you sort of organize your algorithms. And then the piece that we're presenting here is to then tie all that together with custom number systems that have exactly the right amount of precision necessary and the right dynamic range required to get that to get the job done for the computation that the application desires. So this is the introduction of the third incarnation of the Universal Library. We started Universal in 2017 when sort of posits came on board, and we started off as a hardware verification library for posits. But as we were trying to quantify where posits are good and where they're not, you really have to be able to compare them to other numerical values, other representations, and therefore it quickly became obvious that we really needed to broaden that idea of providing a library that has a plug-in replacement for native types, that we also have to support integers and fixed points and floating points and other types of number systems. So that is the introduction, and what we're sort of going to do from this point on is to quickly give you a sampling of the number systems that are currently provided by the Universal Library. They're organized, as you sort of imagined, by their mapping onto the mathematical number sets. And then, of course, as you progress towards the reals, you get more and more creative with doing certain aspects with respect to the sampling or the sampling profile of these number systems. And then one thing that is still a TBD is to create a really powerful oracle, and we're a couple of months away from providing that. But these would basically be sort of adaptive precision implementations where we really could ask very tough questions for numerical reasons, and then use these sort of techniques that Mathieu and Dora and Brad and Zach are working on to sort of inform what type of mixed precision characteristics we would like to drive. So in that context, the way the parameterizations and the specializations take place is really that we like to present these number systems and refine them or present them as parameterizations at the bit level. So the precision is in increments of 1 bit. Dynamic range, of course, depends on the encoding. But then there's also properties with respect to the arithmetic, saturating, non-saturating, and these type of non-linear profiles that would be interesting. And then there's another sort of really important aspect, and that sort of comes to the next layer in integrating these number systems into sort of tensor algebras and so forth, is to leverage user-defined rounding through these fused dot products. So in all of the number systems that are provided by Universal, you can ask for a fused dot product that has some superaccumulator that defers rounding till the assignment of the fused dot product. And then the pieces that we're still sort of working on is this desire to be able to walk up to a fresh code, do some instrumentation of the numerical error, and then inform or use that to inform what type of optimizations and number systems you could apply to try to get to that optimization of minimum energy consumption. So from this point on, what I'll do is I'll do a quick sort of rundown of the number systems that are out there. I'll just focus on the ones that are interesting. Decimal is basically a test number system. Integers are there to really provide a fixed size, fast implementation of an arbitrary integer. These are really interesting for sort of building fast integer type and cryptographic type algorithms. The first one that becomes interesting with respect to the reals is the fixed point. And here we have fixed points that can saturate or not saturate. They're basically a two's complement with a radix bit defined or a radix position defined. And then you can sort of define the efficiency by mapping that onto a block storage device and block storage size, so that if you make these things as elements in matrices, that the matrix layout is as efficient as possible. As I said, it also supports the fused dot product, and the default block size is a byte. The smallest fixed point is 2 bits, and the largest fixed point is basically limited by your memory. The next one up is a classic float. The classic float has been the sort of the thing that was missing in V2, which was really necessary in order to be able to compare posits against sort of the classic float mechanisms. This particular class will encapsulate IEEE, it will encapsulate B floats, it will encapsulate tensor floats from NVIDIA, it will encapsulate the AMD 24-bit and the Pixar 24-bit formats. So this is basically the workhorse if you're interested in classic float type pieces. It has parameterization in terms of the number of bits total, the number of bits in the exponent, the block storage size, and then it has the arithmetic component, the aspects of the encoding that pertain to whether or not the classic float has subnormals, supernormals, and whether or not it implements a saturating or a non-saturating type arithmetic. The smallest C float is a 3-bit float with 1-bit exponent, and currently we're limited to 11 bits because we're a cross-platform implementation, and Windows doesn't support long doubles. So we need to implement a sort of a quick approximation of long doubles to be able to get past that 11, but we'll get there, and we'll support a full 128-bit classic floats. Then we have a sort of an interesting one with respect to trying to capture numerical error, which is called the A real. It's an arbitrary precision real, but it has this uncertainty bit, and we're hoping that will be useful for capturing sort of numerical error going forward. Then we have, of course, the posits where it all started. Everybody knows that piece. The minimum posit we can represent is a 2.0. The largest posit is a 256.5. We can go larger, but performance is not good. The new implementation of the block precision or the block algorithms will make it a lot faster, and we can go up to bigger pieces. And then, of course, we have hardware support for these things as well if you really want to compute with very large posits. Logarithmic number systems, still a work in progress. The valids are another work in progress. They are basically an interval arithmetic using posits. And then we have brought back the unum, which is also incorporated as a mechanism with which we can sort of capture numerical error. The application examples where the universal library is the arithmetic layer is we have an isogeometric engine in Gizmo. We have some CFD codes, the fluid dynamics building blocks. We have MTL4 and 5 linear algebra engines. MTL5 is a proper tensor algebra engine. And then we are really starting to look at posits in particular with FDP in approximation and reproducible signal processing. There's some interesting integrations with quantum simulators, but that really needs some hardware to be interesting. And then, of course, we have the B floats versus posits in the whole AI ecosystem that we would like to influence. So that's really the quick introduction of Universal. We're really trying to build a layer that people can use to develop energy efficient embedded intelligence type applications. And you can sort of look at Universal as becoming a software development kit to develop and test these algorithms. Thank you.
Yeah, great stuff. I'm super excited about Universal. For anybody who doesn't know, I'm an official supporter.
Yeah,
you go to the GitHub page.
True.
I'm an official supporter. I think to keep on schedule for the very last one, we'll put questions over in Slack. But yeah, super excited, and just wanted to emphasize to folks, right? This is all ready to go, right? You can go play with it now, especially if you're in C++. But I think with that, we'll switch back to Pavel to introduce the closing talk. Well, almost closing talk.
Yeah, that's right. So our next speaker, and also the last speaker of the session 5, is Sangeeta Chowdhary. She's a 5th-year PhD student at Rutgers University, working with Santosh. And she's going to be telling us about her research. Broadly speaking, I'd say it's about, how to debug and verify programs with these, how to develop sort of novel abstractions for debugging and verifying programs, and in this case, programs with numerical errors. So Sangeeta, please take it away. We can't hear you.
Can you hear me now?
Yeah, now it's good.
Can you see my screen?
Yes.
All right. So, okay. Thanks, Pavel. Hello, everyone. I'm Sangeeta Chowdhary. I work in Santosh Nagar's research group. And today I'm going to talk about a cool strategy to run shadow execution in parallel. So let me start by giving a high-level overview of my talk. So why do we need another shadow execution tool? So floating point code is everywhere, and so are rounding errors. And we want to comprehensively detect numerical errors in floating point programs. And there is a lot of cool work in this domain. Herbgrind and FPDebug are well-known tools based on shadow execution. And we have also done some prior work called as FP Sanitizer, where we do shadow execution based on compiler instrumentation. And the key idea is to perform shadow execution in lockstep and compare the results. And since shadow execution is done using high precision software simulation of floating point, these tools have a slowdown of more than 100x. Hence, such tools are based on this technique are limited to small programs. And the question which we want to explore in our work is to detect numerical errors comprehensively by performing shadow execution in parallel. So we have inline shadow execution. We want to lift the instrumented code on the side and chop it off to create shadow tasks so that we can run it in parallel on multiple codes. But the challenge is to keep the original program and shadow task in sync and break the dependencies between these shadow tasks. And our key insight is to use the original computed values as an oracle to reset the metadata to break dependencies. The shadow tasks are dependent on the original program for the computed values, but they are independent of each other. Hence, as long as the original program has finished executing, shadow tasks can run in parallel. Since original program is a lot faster than the high precision program, we get scalable speedups. And finally, the last question is, how do we balance the workload fairly among all cores to get scalable speedups? And we use the idea of work stealing, inspired from task parallel programming, to balance the load among all cores. And in the rest of my talk, I'm going to talk about how we have addressed these challenges and what is the cost of our approach. So let me start by giving some background on inline shadow execution. Suppose you have a floating point program and you want to detect numerical bugs in this program. So this figure shows floating point instructions in blue. So how can we detect numerical errors in this program? So one approach could be to write a version of this program with higher precision and compare the output. But the output of both the programs differ significantly, then there is some numerical bug in the program. But this technique won't help in debugging the numerical bugs. And to assist in debugging, we need to compare at various intermediate points. And that's where inline shadow execution can help. In inline shadow execution, we instrument every floating point instruction in lockstep with high precision instruction. And we compare both to compute the numerical error. Once error is detected based on some extra information in metadata, numerical error can be traced back to do the root cause analysis. So now the question is how we can run shadow execution in parallel with the original program. In our approach, we create a new program in higher precision, shown in red in this figure. And each instruction in red mirrors the floating point instruction in blue in high precision. So this approach enables us to run the floating point program in parallel with high precision program on a different core. However, there are a few important questions which you might be thinking of right now. First, how do we execute parallel execution in lockstep with the original program? Ideally, we want to compare every floating point instruction with its mirrored high precision instruction. And to enable that, we instrument the original program to provide the floating point values to the high precision program through buffer. As it can be seen here, the value of first FP instruction is pushed to the buffer. The high precision program starts executing and retrieving these values from the buffer. This enables the execution of high precision program in parallel with the original program, and yet providing the fine-grained comparison to assist in debugging. This approach works well and still provides speed up because FP program is an order of magnitude faster than the high precision program. However, if you are being attentive, then you might be thinking that it is important for the shadow task to follow the same control flow as the original program. And to enforce that, the original program also provides the branch conditions to the shadow program. Our compiler updates the branch instructions to use the branch conditions from the original program. So along with branch conditions, original program also provides the memory addresses to propagate the metadata through memory. Shadow task maps each memory address to a unique address in shadow memory. So this approach with one producer and one consumer can provide some parallelism, but high precision program is so slow that it's not going to be any faster than the inline shadow execution. So we need to slice the shadow execution in small parts to get much higher speedups. And now the question is, how do we split the shadow execution in multiple shadow tasks to get scalable speedups? And this is where we rely on the user. And we ask the user to chop off various parts into multiple shadow tasks. If the user don't create a slice, then the entire program is one shadow task. And to explain that, let's consider a simple program in which main function calls foo function in a loop. So if user wants to do shadow execution on every invocation of function foo in parallel, then user should create a pragma pfSen as shown in red. Our compiler would generate a high precision shadow task, which is foo shadow function in this example. And there would be k shadow task at runtime if the loop in the function main would run k times. Our runtime balances the load using work stealing algorithm and execute the shadow task in parallel on multiple cores. So we create shadow tasks from a sequential program, as you have seen. Hence, shadow tasks are dependent on each other. Now the question is, how do we break the dependencies between these shadow tasks so that they can run in parallel? And to break the dependencies, we need appropriate function arguments and appropriate memory state. And our key idea is to use FP computed values to reset the metadata to break the dependencies among shadow tasks. And let me show you this with an example. Suppose you have a program in which main function calls function foo and bar. And as it can be seen, function bar accesses the memory which was written in function foo. Now, user might want to run shadow execution of function foo and bar in parallel. Hence, user can mark the functions using pfs and pragma as shown in red. So our compiler would automatically generate the code in higher precision and instrument the original program and shadow tasks to communicate via buffer at appropriate points. In this example, for load instruction, our compiler would instrument the original program to provide the memory address which is being accessed and the value read from that memory address. Shadow task bar shadow would read the memory address and the value which was computed in the original program from the buffer. The shadow tasks map each shadow memory address with a high precision value using shadow memory. And each worker thread has its own shadow memory, which is isolated from the shadow memory of other threads. So now coming back to the shadow task in this example, foo shadow writes to the memory location Y. Bar shadow reads this memory location, but it is not updated as write to this memory location was performed by the previous task. Hence, we need a mechanism to detect such scenarios. On every memory access, we need to detect if the value being accessed is produced by the previous shadow task or it has been produced by the same shadow task itself. And to enable us to detect such scenarios, in our metadata, we maintain the value produced by the original program and the real value. If the value being accessed in the memory is produced by the prior shadow task, then metadata won't have the correct original FP value produced by the actual program. Hence, we compare the stored original computed FP value and the value produced by the original program. If they match, then we use the shadow value from the metadata. And if they do not match, then we reset the metadata with original computed FP value. As the later case in this example, and at this point, our metadata is updated and our shadow task can start executing correctly. However, if you have noticed, we have lost the error provenance at this point. And this is the trade-off user has to make to get speed-ups. So to conclude, we are proposing a cool approach to detect and debug numerical errors based on parallel shadow execution. Our tool PFP sanitizer is an order of magnitude faster than the state of the art. We split the sequential high precision program into shadow tasks and break the dependencies between them using original FP computed values. And we plan to explore this idea to isolate other dynamic analysis tools in our future work. With this, I would like to thank you, and you can try our tool. It's publicly available. So thank you.
Great talk. Super exciting. There's a bunch of questions here. Maybe Ganesh, I don't know if you want to kick things off with this question about parallelism.
No, I just was speculating what might be possible more than, yeah, I had to read the paper. Super cool work. I think shadow value is important for so many debugging applications, but the perpetual headache has been, like you said, slow down. So anything to speed up is good. Yeah.
And Pavel was asking, like, how big do we need to make these buffers to keep things from stalling as you go? And you know, what I'm adding on to that, like what latency is added with these frequent buffer writes throughout the execution.
So right now we have 8 million size, default size, buffer size, and anything more than that might add some slowdowns. But we don't keep just one buffer, we keep multiple buffers. So one buffer each shadow task.
Right.
Versus speed up.
I imagine those are pretty fast, right? The buffer writes probably don't actually add a lot of overhead.
The thing was, if producer and consumer, they both are accessing the same buffer at the same time, so we were having this congestion issue. So we have to do this. So producer is very fast. It writes to the buffer very fast, and it's all those values are available for the consumer to consume. So they never touch the same buffer at the same time. Otherwise, it is quite fast.
Right. How do users pick which units to wrap in these pragmas?
Yeah, that's So how we did it is we profiled the application. We took the spec benchmarks and we used gpro, and we identify which are the functions using heavy floating point computations, and we wrap those functions into shadow task. But it would require some kind of intuition from a user point of view. And if user doesn't know anything, user can create one entire program as one slice, and then do kind of a binary search to find what are the regions of the code for shadow analysis, which he or she might be interested in. But it's not automatic right now. This is like the manual effort that user has.
And another question sort of going on here in the chat, sort of following it in real time, is thinking about heterogeneous setups. So, one example is, suppose you had maybe fast cores and slow cores. Like my understanding, the new Apple Silicon has fast cores and slow cores for different trade-offs. What might happen there? Or maybe even going further, what if you, I don't know, had the original computation running on GPU or something, and the shadows running the, or I guess, have you thought about this sort of heterogeneous setting yet?
No, not yet. So everything is running on CPU and multiple cores, and we haven't tested this fast and slow core, and that would
sure.
Some kind of a runtime has to manage it and figure out which is the fast core, but we haven't thought about it yet.
Yeah, I wonder if, I guess like at first blush, I would think you would put the original computation on the fast core and the shadow on the slow, but I guess actually you probably want the opposite.
Yeah, it should be opposite, yes.
Because then they'll almost keep up with each other potentially. And so the total runtime would be better. That's really cool. Okay, well, there is some more discussion going on in the Slack, so folks should head there to keep things going. But I think that wraps up my job as question MC. So let's head back to the main big boss, the MC of MCs, Pavel Pancheha.
All right, Zach, too much. Okay, so this is all, this was all the speakers. So that's the end of the last session. And I think I want to do just a little bit of sort of conclusion and, thanking everyone who participated. So just give me a few minutes to do that. Like basically what I want to say is thank you everyone for coming, for the speakers, for all of the audience, for asking questions, and just sort of coming together and making this happen. So of course, the first group I want to thank is our 20 speakers. I think all of the talks today were really fantastic. I learned a lot of new things, saw a lot of work that I wasn't very familiar with. And I think for me, made a lot of connections between them. And I hope that's true for many of you in the audience as well. So that's kind of the second group here to thank, everyone who asked questions, came and kind of saw the talk, suggested new ways that this work can interact. As I said in the beginning of FPTalks, that's really the goal of FPTalks. We want to make it so that there's more connections, more collaborations, and more sort of awareness of all this different work that's going on in the space and how we can kind of build on that, share techniques, and so on. So I wanted to give a few words about sort of what happens after FPTalks. I mean, of course, I know what happens after FPTalks. You go get dinner or relax or whatever the case may be. But just a few thoughts on sort of where we go forward from here. One thing I mentioned is we have like FP Bench, right? We're trying to build some common resources. A lot of you talked about different benchmarks you used in your work or different ways that these tools can interact. And that's one thing that we want to do in FP Bench. Centralize the benchmarks, make them easier to reuse. And then the other thing I talked about is community building. So you were all here, so you went to this workshop. That's one important part of community building. But there's other ways in which this numerics community comes together. So in particular, I want to highlight, you're all already in the Slack. If you're a speaker, you've been responding to questions on it. If you're not a speaker, you've been asking questions on it. And the Slack is going to stick around. So that's a great place to ask further questions. Maybe that's a quick question about like a paper someone had mentioned. Maybe you want to start a collaboration. Maybe you want to share some recent news or show a paper that's interesting that you found. And the FP Bench Slack is a great way to do that. And then also there's these community meetings. I mentioned them toward the beginning of the talk, but these happen every Thursday at 9 a.m. Pacific. Sorry, every first Thursday of the month. Not every Thursday, that'd be too much. Every first Thursday of the month, so once a month at 9 a.m. Pacific. we'll be announcing those on the FPTalks Slack. If you want an email reminder, let me know. That's a much more informal place where we don't want you to prepare a big talk and practice beforehand. We just want to see some work in progress, get some discussion going, hear something, interesting that's going on. And again, have a way to form these collaborations and, more durable exchange of ideas. So, if you're interested in any of these FPBench resources, you want to contribute benchmarks, or if you want to stay a part of this community, sort of the place that is all organized is fpbench.org. So that's my big takeaway for what I want you to think about coming out of this, and how you can sort of any collaborations, any ideas, any discussion you had here, how that can carry forward. So that's all I had to say. Again, thank you for everyone who participated. Thank you for everyone who spoke. I think I had a fantastic time, and I hope everyone else did too. And that was FPTalks. So thank you all for coming.
And many thanks to Pavel for organizing.
Thank you.
It was a lot of work.
Good job. Hey, bravo.
Good job, Pavel.
Yeah.
Yeah. All right. So again, thank you all. This is all we've got. I think it was pretty good, and let's keep this community going. I'll be sticking around here on Zoom for a couple of more minutes, and then we'll wrap this up.
See you, folks. The Utah group is all lined up. Look at them.
Yeah, we stick together.
Hey, Utah.
Very. Marisa is even wearing a red shirt. How about that?
Yeah.
That's Utah color. Yeah, way to go. And Matthew and Dora are awake at 1:30 a.m. Give them some claps. Kudos.
Yeah, for real.
Yeah, Dora.
Thanks for hanging out the whole time. I really like this event, and I like the community a lot. It's a lot of fun.
Yeah, it's always tough to schedule these things across time zones. So thank you, everyone who kind of reorganized your day to show up.
Absolutely. See you soon, friends. Take care.
Yeah, hope to see many of you in a couple of weeks at the community meeting, and on Slack, sort of going forward. See ya.